So as we discussed last time, the test will be done in the next week for 1 hour, and next hour will be the class. And so the syllabus will be whatever we teach you until today. Okay. So most probably up to stress and relationships, and the book. If you follow the book, the chapter 4 and chapter 5. Okay, this will be your syllabus for the test next week. Okay, now I go to the. I'm sure you are seeing this stress strain relationship. You are seeing this elastic properties of rock. Anybody who has not slept yet? Are you seeing the elastic property of rock?
Yes, sir.
Yes, sir.
So in the last week, I have told you about Hooke's law in 1D, which you already know from your higher secondary class, or even in solid mechanics also they will teach you. Another property, and from there we have told you about one elastic property which is called E, and which is modulus of elasticity. Now I told you also the modulus of elasticity basically, if I can select this red button, there are some average modulus and there will be some secant modulus. There will be I am not able to select this. So there are some average modulus, secant modulus, and there are some tangent modulus. These three types of modulus is there. And I think I explained it to you last time. If this is strain and if this is stress, actually we see something like this. Okay, it's not like that though. It goes like this, and maybe then it comes down. Let me draw it again for you. So if you take a point here and a point here, the maximum, which is we call UCS, and you have already they have already shown you. So the slope of this is basically average modulus. So up to the peak, and from 0 you just. Then if you take a midpoint and join midpoint of UCS, so this is 50% of UCS. And if you join, we normally call it secant modulus, that is like the 50%. And tangent modulus is the at 50% the tangent of this. If you draw a tangent and then find out the slope of that tangent, that will be called the tangent modulus. Okay. So there is three ways we can make. Normally, modulus of elasticity of tangent is greater than secant is greater than average. Okay. Normally, this is what we find. Okay. Now there is another elastic property. This is called Poisson's ratio. This was first observed by a scientist called Poisson a French scientist, and what he observed is when we are pushing or pulling a material, um, it definitely changes its geometrical shape along that direction. That means the length. It also changes laterally. So when I'm applying a load here, definitely this delta will be there, which is we call the deformation. But in this direction, perpendicular to this direction also, it changes. In this case, if it is a cylindrical sample, then it is basically the diameter will change. Okay. So that is the thing what we call the Poisson effect. So similarly, if you pull a solid cylinder, so this will also change in diameter, or the diameter will reduce. So he then said that this Poisson's ratio is basically related to, if I am now doing in the x and y direction, so this epsilon xx will be some mu of epsilon yy. Now this mu is called Poisson's ratio. Okay, this is called Poisson's ratio. Okay, that means the ratio between lateral strain to longitudinal strain. Yy is here longitudinal strain along the application of the load. So that is epsilon yy, and epsilon xx is the lateral. That is the 90-degree apart. So now you can see it can be also in this direction in 3D. So both direction it is possible. So this is called Poisson's ratio. Okay. Now why the minus sign? Can anybody say why minus sign is there? Can you guess why minus sign is there? Anybody? Nobody?
The ratio will always be positive.
Say it again.
So that the ratio is always positive. Because if the axial strain is increasing, the lateral strain will be negative. So it will make the ratio positive.
If the axial strain is compression, lateral strain will be in tension. Okay, or vice versa. If axial strain is tension, then lateral strain will be in compression. So basically, their epsilon xx and epsilon yy, their symbol will be just opposite. And since mu is a material property, it has to be positive. So we have to use a negative sign there, just because of that. Okay. Otherwise, if you're taking the absolute thing, then the negative sign is not required. Okay. So these are the two important properties. One is modulus of elasticity, and another is Poisson's ratio. These are the two important elastic properties. And you already know what is we call isotropy. I think last time I also asked you. Some of you answered. The isotropy is these elastic properties are same in all directions. Okay, then only we will call it isotropy material. And mostly, you know, the rock, they are no way isotropy. Okay, they are all anisotropy. Rock are not homogeneous; they are inhomogeneous. Okay, rocks are not elastic; they are inelastic. So whatever you know, we teach you, it's just the reverse. Rock is just reverse. Okay, but still, we have to first know these properties, and then only we can understand the other properties. So I'm going to tell you a little bit about that part, a little bit about anisotropy. And in this class, we do not go for joint type of analysis. Otherwise, you would have known the full anisotropic behavior of rock. This will be taught to you in advanced rock mechanics class. Okay, now before we proceed further, a simple exercise if you can do, you can read this, it will be good. This one, a concrete pillar of 0.5 meter diameter is reinforced with steel rods. So let me draw it for you. A concrete pillar of 0.5 meter diameter, it's like this, and they have some steel rod here, okay, and rest is concrete. Inside here is all concrete, and there are some steel rods. So the total cross-sectional area of the rods are given, okay, which is 5 into 10 to the power minus 3, should be meter square, not meter to the power 5. The modulus of elasticity of steel and concrete are given. Steel is 200 gigapascal and concrete is 25 gigapascal. Now, considering the composite behavior, determine the fraction of load carried by the steel rods if an axial compressive stress of 2 MPa is applied on the pillar. If we apply a stress of 2 MPa here, how much load is carried out by the steel rod? This is the question. The answer is also given here. So let me explain it to you. The assumption what we will do, all of you have seen a concrete pillar, right? I suppose. Who has not seen one or do not understand what is a concrete pillar? Is anybody there who doesn't understand a concrete pillar? Or everybody understand? Have you seen a house while they are constructing a house? I think most of you have seen. Have you seen how they construct the pillars, vertical pillars?
Yes, sir.
How do they do? How do they do? Imagine you are a civil engineer. How you will do it?
Sir, first they put up the iron rods inside it and then cover it up with concrete.
An iron rod are tied each other, you know, with a square rod
Yeah,
also.
sir, they form a ring of iron to tie them up.
Right. So this is the thing. Now, do you know why they put those rods? And it's a very negligible area. See, there also I have given in that problem. It's a very negligible area. See, with the total concrete volume and the volume
Yes.
of that rod is very negligible. But still, why do they put this?
Sir, because sometimes from the temperature they expand or contract the concrete, maybe because of that they put steel so it can hold up.
Okay, that may be one. And another is, if you can solve this problem, you will know why. Okay. So now what is happening is, see, you see the negligible area it is taking 5 into 10 to the power minus 3 meters square. Okay, it's very little, and total area is 5 total area of the pillar by 4 0.5 square, right? So this is the total diameter, isn't it? This is the total area. Now this equals to area of the concrete plus area of the steel rod, right? So area of the steel rod is given, so you will be able to calculate the total area of the concrete where the load is being applied. Sorry, not load, the stress is being applied. Okay. Now, the assumption, what we are doing here is this or this above one, that the deflection of the steel rods are equals to the deflection of the concrete. That means the deformation, what is happening in the steel rod, will be the same. Otherwise, क्या होगा? If the deflection of the concrete is more, then तो ये ऊंचा नीचा हो जाएगा. So it will not happen. So rod and concrete will deform in the same rate or the same value. So if I now know the strain, if I can find out the strain, so the strain of concrete, can anybody tell me what it will be? Strain of concrete? This is our Hooke's law. Strain of steel will be load on steel by modulus of elasticity of steel. Here, another assumption is we are omitting the Poisson's ratio at this point of time. We are just considering it's a 2D problem. Okay. So you see, strain of concrete is equals to strain of steel. Now, since deflections are same, so this length is, let's say, some length L. So deflection will be, let me delete that. So the deflection will be delta of C will be epsilon C into L, and delta of S will be epsilon S into L. This is it. Okay. Now these two are same. Okay, they are equal. So if they are equal, we are finding out the stress on the steel is related to that. Okay. So stress on the steel is related to that. Now the total load. Okay. The total load will be given like this. Stress on the steel into area of steel. Stress on the concrete into area of concrete. Okay. So if you now equate this to equation, we will find this. Okay. We'll find that. Now I already gave you the total area, you already know. So you can find out the areas, area of the concrete. So once you know the area of the concrete, you can find out sigma S. That means stress on the steel. It is 13.58 MPa. And you see stress on the concrete, it's very low. You know, this is the reason, because we want major load to be carried out by those rods, not by the concrete. If you give too much stress on the concrete, it will fail. So rod carries the load. Okay. Now if you change to the load, then this becomes, if you change to the load, that means in meganewton, then since its area is very low, so it will be, but still it is about 0.173 times of the total load. This is what. So you see the area is very low, 0.005. Okay, but it carries a huge amount of load because it carries very high stress, and that's why those rods are given. There is another reason those rods are given if there is any lateral movement, let's say earthquake, then also it protects, because concrete will give you zero protection in earthquake type of loading, means in a dynamic loading, but rod will help you there. It will protect you in tension. Okay. In compression, it takes the majority load. In tension, it protects you from complete collapse. Okay. That's why they call it reinforced cement concrete, RCC. Okay. And that's why we do not use PCC, which is basically this Portland cement concrete, just concrete pillar. We always use reinforced. Okay. So this is just an example why we need this rod. Okay, I think the isotropy and all these things are already explained to you. Now, if I have to generalize this equation, if I have to generalize the Hooke's law, how do I do? Let's see this cube, what is happening, and we assume in this cube the modulus and modulus of elasticity and Poisson's ratio are same in all directions. Means in x direction also E mu, here also E mu, here is also E mu. In all direction, they are remaining the same. So it's an isotropic material. Okay. So I now consider in the x direction. So I'm looking at the strain in this direction. So that is my epsilon xx. So definitely by Hooke's law, I will say this is sigma xx by E. Right? This is my strain in x direction. But you see, there is a sigma yy acting in this direction. So if sigma yy act in this direction, what will happen to epsilon xx? According to Poisson's effect, we will say this will be right. Everybody got that? So there is another epsilon xx due to sigma yy. Similarly, there will be another epsilon xx due to sigma zz. Okay, this is the effect of the Poisson. So now we can add them together, and if we add them together, basically it's what we call the superimposing concept. So finally, epsilon xx will become sigma xx by E minus mu by E sigma yy minus mu by E. Okay. In other words, normal strain in x direction also now depend on normal stresses in perpendicular two directions. Okay, plus its elastic properties. That will be depending on that. Similarly, I can write epsilon yy and epsilon zz, and that's what is written here. Okay, so see, epsilon xx we can write it like that, and epsilon yy, epsilon zz we can write this form. Okay. Now, what happened to shear strain? Now, in the book, it is given how to prove that. In shear strain is simply related to the shear stress by a modulus called modulus of rigidity, or some people even call shear modulus. G is also called shear modulus. Okay. G is also called shear modulus or modulus of rigidity. Now, the proof of this I'm not sure whether it is there, otherwise it is given in the book. How it is related, G is equals to E by 2 into 1 plus mu. This requires the knowledge of Mohr circle. Okay. So by Mohr circle we can very easily can show this relationship. So now if I put all of them together, epsilon xx, epsilon yy, epsilon zz, gamma xy, gamma yz, gamma zx, and this side, if I put sigma xx, sigma yy, and all these, then I find a relationship like this. It's just putting this thing in a matrix form. So this is becoming generalized Hooke's law, and this matrix is called the compliance matrix, which relates between strain and stress. So this is strain tensors and stress tensors. And this, if you are looking in the tensor form, it's a fourth order tensor, we call it. But I'm not going into that direction. So there is a relationship between strain and stress in 3 dimensions in elasticity. Remember that. In plasticity, this relationship doesn't hold true. Okay, it is completely different. In elasticity, this is the relationship. Now, any questions so far before I go next? Everybody understood how this generalized Hooke's law has come? Especially the matrix, compliance matrix. No question. Everybody understood. Very good. Now, before I go into this, if I explain this little in little detail, you see this matrix C, this one 1 by E, this whatever written. What do you see about this matrix? Do you see any property of this matrix? Anybody see any property?
Symmetric matrix.
Symmetric.
Okay, so symmetric matrix first. Okay, and second thing, we call it positive definite matrix. All the diagonal position will be non-zero. Okay, that means diagonal position will be non-zero and positive. Okay, they will not be zero. Also, negative तो नहीं हो सकता है. It is positive and non-zero. Okay, so or non-negative, I should say. It is basically non-negative. Now, a positive definite matrix has a very interesting characteristic that it is invertible. Okay, so this matrix is invertible, and if we invert, then relationship is between stress and strain. So the stress and strain, when we invert, we get a relationship like this, and this is called constitutive matrix. So do not, forget this term constitutive. It is basically coming from constitution. Okay, and you know why it calls constitution or constitutive? Because like any to run a country, you need a constitution, right? In a democratic country. Similarly, to understand the material behavior, you need to understand this matrix T. Okay, and not only that, in plasticity also there will be a constitutive matrix. Means how the pillars, or in this case, basically the strain and stress, these are the two pillars of elastic variables. Now how these two important elastic variables are related to each other, and that's why it's called constitutive matrix. This is how material behaves. Okay, for a isotropic elastic material. Now here is also same. You can see they are all non-negative in the diagonal position. Another thing you will notice that we are, since it's a isotropic, we are using only two parameters. Out of this diagonal, whichever you take, the total 21 position you can fill, out of which is 9 positions are basically non-zero and 12 positions are 0. So what it is basically saying us that shear stress tau xy does not depend on epsilon xx. So shear stress has no relationship with epsilon xx. Sam, I am in a class, so okay, take it. Yeah. I'm here. So there is no relationship here. It is 0. Okay, that is the parameter 0. They are saying there is no relation. So is it true for all cases? Absolutely not. This is for isotropic elasticity. It is true. But if you go to anisotropic elasticity, it is not true. Okay, there will be some value. That means shear stress in xy plane will depend on the normal strain in x direction. Okay. So actually all should be non-zero, but this is a very special case. Okay, and we are only using two parameters. One is E and one is mu. This is for isotropic. Okay, so this is what you need to know. Now, using E and mu, these two elastic properties, some other properties are derived. One is called bulk modulus, which is very important, and another is called Lamé constant. The bulk modulus, they relates between pressure or the average stress. This is, I define as something called sigma m. Sigma x plus sigma y plus sigma zz by 3. Now, I defined a average normal stress. So this average normal stress divided by volumetric strain is basically K. That is the bulk modulus. Okay, and if you put them together, this is the relationship will come. E by 3 into 1 plus 2 mu. And Lamé constant is a particular constant which is important here. You can see what is Lamé constant. This is Lamé constant other than the mu. Okay, see in Lamé constant there is a mu. Okay, so there are also many other relations, but these are the main important thing. So one is E mu. Oh, sorry. One is E mu. Another is G and K. Okay, these are the two, or E mu. They are important relationship for us. So everybody understood? Now, the important thing is what will be the value of the maximum value of mu? Can anybody tell me now? What could be the maximum value of mu? Quotient ratio.
So 1 by 2.
Yeah, 0.5. In elasticity, quotient ratio is not above 0.5. Okay. For any solid material which behave elastic manner, will not exceed 0.5. Now you can see why it is. It is 1 minus 2 mu is sitting there. Okay. And there are some other reasons also. Now, two important concepts regarding the constitutive relation in 2D. So far you know 1D and 3D. 1D is epsilon is equals to sigma by E. Okay, there is no partial step. And another you found epsilon is equals to C into sigma. Okay, this is tensor. So this is in 3D. Now what happened in 2D? Now once we say the value or the constitutive matrix in 2D, we have to understand that at what purpose we want this 2D analysis to be done. Now there are three possibilities. One of them is called plane stress, another is plane strain, and another is axisymmetry. Now what is plane stress? Now let's say this is a steel plate and we made a hole. Okay. Then I applied the stress in X and Y direction only. Okay. There is no stress applied in Z direction. The application of stress is only in X and Y direction. So external stresses or external load are applied on a plane. In this case, XY plane. Okay. Then the thickness of this plate is very small as compared to the width and height of this, whatever we are testing. It's pretty small. Thickness T is very small. So what will happen is now, you can see, because of this stress, okay, there will be a deflection in this direction. Let me give you an example. You take your book and you put it vertically and give load from the top. You will see the book deflects in third dimension, okay, in the out of plane direction. So that's what the deflection, that means a UZ may occur in that direction. Okay. Why this UZ will come? So definitely, if there is a UZ, there is a strain. So epsilon ZZ is non-zero. This is not zero. Okay. Even if I've given the load in X and Y direction, the strain will occur because there will be a deflection in out of plane direction. And since there will be a displacement in this direction and there is no protection, no kind of force or any constraint is given in out of plane direction, so sigma ZZ will be 0. If this is the condition, and definitely the other shear stress, tau YZ, tau ZX, they will be all 0. So as the strain, because there is no Z axis, so there is this cannot occur. So only thing is epsilon ZZ will be non-zero, and in that case, this will be called as a plane stress condition. As the name suggests, this is stress is generated only on that plane where the load has been applied. There is no stress developed in out of plane direction, but strain will be possible. Okay. So if we assume that condition, then whether you analyze this with 3D or you analyze with 2D, the results will be exactly the same. And that's why this is called plane stress condition. Now you see, how do I get this? I collapse everything. If I now go in the general life, you just see this matrix, whatever is here, and you see this. See what I have taken, only these four. Okay. Only I have taken this four. And here just the epsilon ZZ is written after this. Since it's a out of plane, so this is written at the end, but rest everything remains. Okay, and here this you should see. You already put 0 because we know sigma ZZ will be 0. Okay, this is sigma ZZ. So if this is 0, now you can see the epsilon ZZ. You can find out what is that value. Is this. Okay. Now, if you just make the constitutive matrix, just invert that, and you will find a matrix like this. Okay. So this is, if you want to apply in 2D, one of the option is plane stress. And what is the condition? Your thickness is much less than the width and the height. Now, what is the example? Okay, let me give an example. See, a thin pipe, a hole in a thin plate. Okay, if you want to test. Now, let me give you the example, a real life example. You know the aircraft wing. Okay, if you want to test the aircraft wing under tension load, we normally test it like this, the way we have given here. Here it is given just compression, but in that case the load will be given in tension. And you can see this is a thin plate, aircraft wing, or a car body. Okay, the outside body. Okay, this is a thin plate. So they are all plane stress conditions. Okay, if you want to analyze in 2D, there will be all plane stress conditions. Or you can do in 3D, doesn't matter. Okay. So those are the examples of plane stress. So you may be wondering then, where are we in the mining and geology cases? Where are we? So ours is basically plane strain. Now what is plane strain? Now you see, we build a tunnel, right? This is my rock mass. By the way, do you know what is the meaning of rock mass? Has this already been told to you? Rock and rock mass.
Sir, rock mass
Yes,
is
sir.
inside the earth, and rock is
Okay.
what we get on surface.
Say it again. I didn't get it. Rock mass is?
So rock is what we get on surface, and rock mass inside the earth surface.
Okay. Anybody else? Everybody has this definition. Okay. One time, I think, I don't know, about 4 or 5 years ago, maybe 3 years ago, I asked the similar in this class. So one answer came very interesting. You cannot imagine that answer. It says, sir, the rock which has mass is called rock mass. Do you agree to that? The rock which has mass will be called rock mass.
So
No,
every rock
yes.
will have.
Any rock will have mass. So rock mass is what you see in the field. Okay. This I'm not sure. Next time you must see wherever you see a exposed surface, how the rock conditions are. You'll be seeing full of jointed, fractured. You know, this that we are talking about anisotropy in homogeneous. You will see there, and that is what is rock mass. And from there, the intake part, where there is no joint, fracture, anything, that is called the intact rock or only rock. Okay. So I will, or I think Professor Verma will do that rock mass classification. Then he will give you a detailed definition of all this. So let's assume now a tunnel has been built in rock or in rock mass, doesn't matter. Again, tunnel axis is z-axis and xy is any plane cutting it vertically. Okay. So as before, here again, if I take only a plane, so load is applied in x and y direction only. This is x, this is y, and this is basically z. So in z direction, that means in this direction no load is applied, no stress is being applied. This is what we are assuming. If this is the condition, and now the length of this tunnel is much higher, let's say 500 meter, 1 kilometer. Okay, it's much higher. It's not that very thin. Then it will be considered as a plane strain condition. The reason is, even if the stress is applied in x and y direction, because of this mass in z direction, this load will not be able to deform it in z direction or the out of plane direction. So if there is no uz, this is 0, then this also comes 0. However, this 0 means there is a particular stress which made it 0. It didn't allow it to have that deformation uz. And that's why sigma zz will be non-zero. And that is why, as the name suggests, all the strains will be in that plane. There will be no out of plane strain. And that's why it is called plane strain condition. Okay. Now, when you apply this condition, then this become like this. Now you can see the difference. Okay. You see here sigma zz and here 0 because epsilon zz is 0. Now you see just the plane stress. It just here it is 0 and here it is epsilon z. Rest this matrix is same. Okay. So now sigma zz I can estimate it's like this. Okay. So there will be a out of plane strain, out of plane stress and out of plane strain will be. Okay, and rest whatever is the shear strain and shear stress belonging to z direction will be 0. Okay, just a minute. Hello? Good timing. क्या क्या Mega net. ওটা আছে আচ্ছা ফাইলে নেই আচ্ছা ঠিক আছে okay so this is the plane strain okay so everybody understood these two difference okay let's see this exercise and then first exercise do not see that I'm not sure how to block this show that the ratio of uniform horizontal stress to vertical stress at a point below the ground equals to this let's say this is the some h distance below this is surface this h distance below now there is a vertical stress sigma b does anybody know what will be this sigma b let's say both of them are sigma h then saying prove that sigma h by sigma b is mu by 1 minus mu where mu is there is a material right there is a rock here so Poisson's ratio is mu can you prove that without seeing this okay this is the question does anybody know what will be sigma b in situ stress तो अभी कर लिया what will be
Sir,
sigma
rho
b
GH.
rho gh बाकी किसी को कुछ पता नहीं है क्या who are the people let me call one person Anup Singh are you there और खाना खा के सो गया Anup Singh not there Aryan Chandani nobody is there okay let me see who else are there Aditya Raj who is there Aryan Chandani I'm not able to hear you okay Aditya Raj your microphone is not good okay Alok Kumar Amardeep nobody is there so only Saurabh Chaudhary is there nobody else who else are there you put your hand let's see how many are there okay now how many people are showing okay Aniruddha Jadhav tell me
Yes, sir.
Yeah, tell me. Why it is gamma rho, sorry, gamma or rho GH? Bobby?
So rho is the density of Earth, so rho GH leads to pressure.
Hmm?
And we take rho as the average density of the Earth. So like so it becomes rho GH.
Now rho is the average density. Then why it is rho GH? Sigma B.
So, like in class 12, we can assume a volume until where we want to take a pressure. So we will find that rho into volume will be the mass, and the force will be mgh by A. It will give us rho gh.
This is the area A, right?
Yes, sir.
So we are talking about stress on this area A. So what is the total force acting on this area A? Vertical force?
Rho gh into A.
Rho GH into A. Divided by A. Limit A tends to 0. What it is?
Rho gh.
Right. So this is the definition of stress, right? Force per area when area tends to 0. Because we are trying to say it is at a point. Okay. So these become rho GH. Now, does Professor Verma say what is horizontal stress? Do you think there is a horizontal stress? Okay, let me ask you this way. Who else are there? Many people. Amlipur, you also put your hand, I guess, so you are there. Priyank Seth, you are also there?
Yes, sir.
You are there. Okay. Now, if this is not rock, if this is, let's say, water, then what would have been horizontal stress? Vertical stress remain rho GH, and rho is here
Yes,
what? 1000 for water, let's assume.
sir, it
So
would
what?
have been the same.
It would have been the same. Okay, because liquid give equal pressure, right?
Yeah,
Now, do you think rock will give more or less?
sir, more. Sir,
Rock will
more.
give more horizontally.
Sir, because of tectonic movements also
No,
that take place.
tectonic. I'm not talking about tectonic at all. I'm talking just geostatic. Just because of this static condition. Tectonic is a
Uh,
different story altogether.
Sir, we can think like in water, the particles are free to move, but in rock, they also exert the opposite reaction to them. Like there is not so much room to expand in rock. So the
तो
boundaries
काम
also.
तो कम होगा या ज्यादा होगा?
Huh?
हॉरिजॉन्टल स्ट्रेस कम होगा या ज्यादा होगा पार्टिकल से?
सर ज्यादा होगा.
ज्यादा होगा. ओके. अम्लीपुर कम होगा ज्यादा होगा? इन सॉलिड.
Sir, vertical stress will be more.
Particle stress will be more. Okay, he is playing very safe. Anybody else can say कम होगा या ज्यादा होगा? Who else are there? कौन कौन हाथ उठाया था? मोहित, तुम हाथ उठाया था क्या? नहीं नहीं है भाई. Who else are there? Aniruddha Jadhav. I think you have already said, right? Anybody else who can answer? कम या ज्यादा? One more.
Sir, vertical will be more.
Vertical will be more. Now, can you tell me by what elastic property it controls, a more or less? There are two, modulus of elasticity and Poisson ratio. Which one will happen?
Sir, Poisson's ratio.
Yes, it's the Poisson's ratio. That's why you see the problem. This is depend on mu by 1 minus mu. Okay. Now you can see if in water, if they are same, what is the mu? If water they are same, what will be the mu of water?
0.5.
0.5. So that is the limit. Okay. This solid will be more than, less than that. Okay, because this ratio is less than, this ratio is less than 1. Okay. So now the mu, the maximum limit is, that's why we say 0.5. Because when you're going to 0.5 means your density is more or less going towards 1000. But our density is much more. So the more the denser material, okay, what will happen? Okay, density we come to later, otherwise you will get more confused. So you understood this. This will be for water, mu is 0.5. Okay. Now for solid, what will happen is, we'll write this equation. Let's say we take any one, I take another color. Any one is Z, this direction, and this is X, and this is Y. Let's say. Okay, any one. So if I put epsilon ZZ, because in a below ground, you will consider this stress is generated because, is simply because the strain has been put to 0. Okay, so it is, now we are in plane strain condition because we are looking at 2D. So we have a sigma B here and we have a sigma H here, and this out of plane sigma H will be there, but epsilon that ZZ will be 0. So when you put that, then this is epsilon, this is sigma H, this is also sigma H, and this becomes sigma B. And when you do that, they relate to this. Here only assumption is both the horizontal stresses are considered to be the same, okay, which is not basically, but in this calculation it is assumed. Now you can see since our Poisson's ratio become point less than 0.5, let's say 0.25. So if it is 0.25, these become 0.75, which is 1/3. So our vertical stress is always higher than the horizontal stress. What stress it is? It is the geostatic stress. Remember that, geostatic horizontal stress. Now one student has said it's a tectonic, it will be more, of course. Normally horizontal stress is much higher than the vertical stress. Especially in the shallow depth, it is much higher. At a very greater depth, let's say almost 1 kilometer, below 1 kilometer, they are more or less getting equal. Okay, means we say the hydrostatic condition prevails below maybe 1 kilometer or kilometer. They are more or less same. Now here, why we are saying this is less than 0.5? One of the reason is all rocks are porous. Okay, whatever may be the compaction is there, but still it is porous. And since they are porous, so the porous material will have less Poisson ratio. Okay, and since water is, we can consider they are completely one molecule to one molecule, they are all are very much compact, means connected to each other. So there is no porosity in water. So they are 0.5. And any other solid material will be less than 0.5. Okay, is that clear? There is another problem. This is given in the book. I think you solve it in your home. And if you cannot do it, then you just let me know or let them know also. They will solve it for you. This is given in book, and I have taken it 5.4. Now there is another way of doing 2D also, which is called axisymmetry. Okay. So the axisymmetric condition is like this. Has Professor Eddie told you about shaft, mine shaft? Do you know already what is mine shaft?
No, sir.
Okay.
Okay.
Okay. How many of you have seen a tunnel? Or you have been to a metro in underground? Anybody have been to a metro in underground? Okay, Saurabh Chaudhary went. Only Saurabh? Nobody else? PP. Who is PP? Aja, Aman Goswami also went to a metro. Now, Akash also went. Who else has went? Now I will ask, maybe, who is that? Priyanjit Poddar, he also went. Okay. So about 4 or 5 students has gone to a metro station. Now let me ask, okay, Poddar, you please describe what you have seen when you went underground.
Sir, as in, so like there is space for the metro to move, and the inside of the tunnel is covered with concrete, I guess.
Okay. Good observation. See, next time, let me tell you, you all are going to become engineer. And you know the difference between engineer and anybody, any other profession? The engineer has to observe. Okay. This is the other people may be seeing the thing, and you have to observe. And you have to be Sherlock Holmes. Okay. Not that great detail, but since you will be becoming a mining guy, so you have to see the rock, you know, how this rock is formed like this and how they have made a tunnel in a rock like that, and it is still standing, nothing happens. So like you have seen a concrete, lining, we technically call it concrete lining. So if you could have seen beyond that lining, you have seen the rock which have been either blasted or excavated by a machine, and then they put that line. Okay, that lining is nothing but what we call is a support system. Okay, rock is want to deform because they have created a tunnel. And the moment you have created an opening, I will come to, after I complete this, we'll come to the stresses in underground opening. So they want to deform. But because they put a lining around this, you know, which is very good concrete material and all this. So this is giving a pressure so that it doesn't come. So normally the most safe shape of the tunnel is circular. The safest one is circular. Okay. Circular tunnel. Now this can be 1 kilometer or 2 kilometer long, a circular, but hardly we can make a circular. So we make a D shape, something like this. Okay. Or if that is also not possible, then rectangular shape. Okay, it's very easy to make. But for making a circular, you need a machine, and this will be the most stable. You will know later on why. Now, consider a vertical tunnel. Okay, you have probably seen the horizontal because metro you have entered through a either through a you didn't use lift. What you call is a incline. You went like this. There is a staircase. You went this we call incline in mining term. See, we all everything in mining because these things comes from mines only. This concept. So there is an incline, and by which you come to this tunnel. Now you assume this tunnel become vertical, and it looks like this. Then it is called a mine shaft or a lift. Then we put a lift there and we go up and down. Okay. So this is called shaft or a mine shaft, which is the diameter here will be about 6 meters, 5 to 6 meter diameter. It's a huge, big shaft. Okay. Now in an axisymmetric condition, if this is a perfect circle and load is again applied in a particular plane, or we can also apply vertically here on top of this annulus. Okay, this thing is raw. Okay, this is raw. Only this inside this thing is hollow, and that is what is the shaft. And then this will be considered as a axisymmetric condition. So let me show you if I delete them. This is my symmetric axis. So how it become 2D? Let's say I'm taking this. This is my rock. Now load may be applied something like that. Maybe it has applied also here. Now this is maybe, let's say, x-axis, and this may be y-axis. So this still become 2D. Now you can rotate this 360 degrees. So what it becomes? It becomes this shaft. Or similarly, for tunnel also you can do the same. Only it will be in the horizon. Okay. So it is a 3D problem, but we have made it into a 2D. But there are some this kind of conditions need to be applied. Then only you will be able to make it. Now, in that particular case, what it is showing here is there will be four stress. One is sigma yy along the that symmetrical axis. There will be sigma rr, which is the radial stress, we call it. It becomes basically r, radially coming out. Radial means it is now in all direction, right? It is in all directions. So it is radially coming out. That's why it is called sigma rr. And there is a thing called sigma theta theta, which we call tangential stress along this. Okay, that's called tangential stress, or some people call hoop stress. This is also used in thick pipeline, let's say gas pipeline or water pipeline. The thick one will also have this hoop stress. And there will be a shear stress along this top and also along here. So if this is the condition, then we will consider is in a axisymmetric. We can reduce into 2 dimension and then just rotate 360. So here the calculation of strain, as you can see, sigma epsilon yy will be del uy. So my displacement is this, and this is the displacement. Two displacements are there. Sigma theta theta is basically the hoop strain, and this is change in the perimeter. Okay, that is what is happening. This is the original perimeter at any distance r. This is the original perimeter 2 pi r, and this is with displacement ur. So it becomes ur by r. Shear thing remains the same, and this will be, oh sorry, this is epsilon yy del b, sorry, I have written mistake, this is b. So epsilon yy del b by del y, this remains the same. This is just del ur by del r. So the strain definition become little different than plane strain. You can see that, and but the constitutive matrix remains the same as plane strain. Okay. So now here stress also sigma rr, sigma theta theta, tau r theta, sigma yy, and so by reducing this one dimension, the calculation become very simplified. You can see there is a 6 by 6 matrix become 4 cross 4, so 36 becomes 16. So the huge computational burden is gone. Okay, by reducing this one dimension. So we can reduce the 3D problem into 2D by 3 ways. One is plane stress, one is plane strain, and another is axisymmetric condition, which is given here. Okay. So now I will tell you another thing, which is I promised you that the relationship between some anisotropy, and this is not here, but oh, okay, it is there. Transverse elasticity is there. Very good. So this is called linear transverse isotropy, which is also an anisotropic condition. Now let me give you the figure. As you know, the coal deposits happen due to a sedimentary formation. Now, in your geology, they are going to, you know how many different type of rocks are there? In geology, they told you?
3, sir.
Number 1.
Sir, igneous, sedimentary, and metamorphic.
Okay, there is one sedimentary, right? Now, the sedimentary means they have deposited sediment-wise, means one layer by one layer. Right? Now, let's say this is one layer, layer 2 and layer 1, okay? The 2 layer. And this is how they have deposited. Now, I take a core along this, I take a core along this. I told you the drilling, and I take a core along this. Okay, so 2 horizontal direction and one vertical direction, because vertical direction is nothing but the depositional direction. Now, what will happen is if you test it in the laboratory, you will see maybe in X and Y direction here, the property may be same. It may not be, okay, but still we can assume this is the isotropy axis. We can still assume this is the isotropy axis. But this one, this direction, the properties will be definitely different. So that's why we have said in this direction it is E2 mu2 and these two direction is E1 mu1. So we are saying we have an isotropy plane. Okay, there is a plane of isotropy where properties are saying in all the direction along that plane, but perpendicular to that plane, properties are different. The elastic properties are different. So if the isotropic properties is E1 mu1, then anisotropic property is E2 mu2. Okay. If that is the condition, then we will call it linear transverse isotropy. Transverse meaning the 90 degree. So it's a still linear material. So we call it linear transverse isotropy. And this is the first form of anisotropy, I must say. Now the compliance matrix will change to this. Okay, the compliance matrix changes to this. Now you see in the Z direction it becomes mu2, not mu1 anymore. And this will be mu2, E2, and all these things is changed. Okay, and rest of the thing you will get in the book, the rest of the formula and all these things is no required to mention here. So this is what we call linear transverse isotropy. Remember that it is for sedimentary formation. This is quite possible and it is happening also. Okay. Okay. Now the last part of this, before we do some examples, the last part of this is called plasticity. Now, I told you earlier that this is stress and this is strain. I'm drawing like a Hooke's characteristics. Now, after this, it can go this way, it can go this way, it can just fall like this. Okay. There are basically 3 paths it can take. If the stress still increases, means after yielding, if the stress still increases with strain, but not at the same rate, the rate gets down, then this is called strain hardening condition. If the stress continue to go down, okay, as the strain increases, then we call it strain softening. Okay, this is called strain softening behavior. So this is called strain hardening behavior. Stress is increasing with strain after the yielding. However, rate is not same. How do you know rate is not same? Because this rate is going like this. Now it is like that. And if it is continually go down, we call it strain softening. Okay. And if it is abruptly fails, just lose its stress instantaneously, we call it brittle. We also call it ductile. So that is the ductile behavior. This is brittle behavior. There is another behavior which is basically more or less theoretical. This may go straight. And this is called pure plastic. When it is straight, when stress doesn't increase or decrease as the strain increases, then it is called pure plastic behavior. Okay. So after yielding, 4 possibilities. Mainly 3. Pure plastic is basically theoretical. One is ductile or strain hardening. One is strain softening, and another is brittle. And pure plastic is, it doesn't increase or decrease the stress, doesn't increase or decrease. Okay. Now, let me ask you. You tell me the gold. Is it a ductile material or a brittle material or a strain softening material? There is a particular reason why I asked for gold. What is this material? That's a copper. Nobody?
Sir, gold is ductile.
Gold is ductile. Very good. Okay. Anybody else? I will ask you the reason. Okay. This is Muhammad Shahiyar, right? Shahiyar. Okay. Anybody else? Gold is ductile or not?
Yes, sir, it is ductile.
Okay. Now, you two tell me why. Not why. How do you know?
All metals are,
How do you know it is ductile?
all metals are ductile mostly.
Huh?
So
Sir,
mostly all
because it
metals
can
are
be drawn
ductile.
into wires easily.
No, no. Priyansh is saying. Priyansh, go ahead.
Sir, because it can be drawn into thin wires easily.
Yes, very nice. Very good. This is the reason. See, Gold, you know why gold is so highly priced? Can you give me the reason?
Sir, it is non-corrosive and
Number
highly
one,
ductile.
and highly ductile.
And a good conductor of electricity as well, I guess.
No,
No, no,
that,
sir, it is silver. It is silver. Sorry, sir.
no. Gold is, and also it is shiny.
Yeah, lustrous.
Okay. Yeah. So, but you know, gold is high priced because you can make a thin wire with a very less amount of, you know, mass, very less quantity. Even you can see a yarning can be made with 2 gram, just 2 gram. Okay, they can make so much thin wire. No other material can be made like that. Okay, so it keep on increasing its stress. It will not tear up. See, the next best metal is copper. You can also make very thin. Also silver a little bit. That's why these three metals are so much, you know, in demand, especially in the form of jewelry. This is a very interesting properties that even if after yield, it doesn't lose its strength. So that's very good. But for that you have to put little bit of, you know, impurity in the gold also, and then only its strength little bit increases. And another thing, remember the gold specific gravity is 15. Okay, so it's a very dense material. So even you can change in the volume very easily, and that material has that property. That metal has that property to make it like this. So as copper and so as silver. Okay. Now reverse or the vice versa is glass. You see, that's brittle. The moment it breaks, it cannot take any further load. It just gone. Okay, you cannot apply any further load the moment it breaks. So means it will become like a very small pieces. Our rock is somewhere in between. Most of the rocks are strain softening. It's gradually shedded load, but there are some granite. It's like a brittle. And some igneous formations are highly brittle. Um, marble is not so, but marble is also, some marbles are very brittle. Okay, once it's cracked, you know, it is gone. We normally say, and its valuation just goes down just like anything. Otherwise, marble is very expensive. Now, if this is how it behaves, so for a strain hardening behavior, what happened after yield? What happened after yield? This we wanted to know. So let's say this is the drawing I have given here. Up to this point, we have elasticity. Okay. Now let's say the load has increased from sigma y e to sigma b. Let's say it has increased, or I have given that point A to point B. Okay, fine. So if point A to point B, the stress has increased. Now what happened here is, see, when it is increased from point A to point B, let's say this is I am defining as a delta sigma. Okay, this is the change of stress. Means delta sigma is nothing but sigma B minus sigma A. So when it has increased there, the strain has increased from this place to this place. Okay, this is the total strain increment. Now we assume This has now two components. One is elastic part and one is plastic part. One is elastic part and another is plastic part. Okay, this is the two component. Now, why I am saying this? What is the purpose of this strain increment? Elastic strain increment. This is the elastic part, and this is the plastic part. Now, the purpose of the elastic strain is to change the stress, right? That is what Hooke says. That a strain will change because of the stress only, especially if it is the elastic strain. So this must have changed since my stress is also increased. So I can say this is due to this one only. So the change of stress has occurred according to Hooke is by this elastic part. Now, if I take the total one, then the stress increment will be very high, isn't it? Stress increment is this, but stress has increased only up to point B. If I take the full one, then stress is all the way up to this, from here to here. So, since it's up to B, so it must be only the elastic part. So, that is the part which is written here. Okay, by this. So, what I do is, then I make a parallel line to this. So this much is my elastic strain and this is my delta sigma. Okay. Now suppose we have a tangential modulus Et of this line. So we will also write this equals to Et into the total strain. Okay, this total strain. So this is the elastic part, elastic modulus, and this is the tangential modulus after yielding. Another one we can say, this is hypothetical, remember that. This H parameter is called hypothetical hardening parameter, or we call it strain hardening parameter, we call it. And that is multiplied with epsilon P. Okay, with the plus. Actually, the strain hardening parameter they doesn't contribute to the stress. I'll tell you what it does. It doesn't contribute to the stress. So now, with these three equations here and another equation here, we can very well write a relationship like this. We can very well write a relationship. We can derive a relationship like Et is equals to E into 1 minus E by E plus H. This is for one dimensional. The same is true for three dimensional also, but I am showing you for just for one dimensional case. Okay. Now, what you will see here that this modulus, if it has to be greater than 0, then what will be the H? Greater than 0 or less than 0? If it is to be greater than 0, then what will be the H? It also needs to be greater than 0, right? If it is to be less than 0, then H is to be less than 0. Isn't it? And finally, if it is to be 0, then H is to be 0. Okay. So this is what the hardening modulus play into here. So now we normally define If ET is greater than 0, that means it is strain hardening. If ET is less than 0, it will be strain softening. And if ET is equals to 0 or the hardening parameter is 0, we call it pure plastic. This is straight line. So the slope of this line is 0. And here slope of this line is positive. Here slope of this line is negative. Okay. Now, this is a serious analysis ramification as far as deformation in plasticity is concerned. But this is beyond the your syllabus. We will not discuss plasticity anymore in this class. This is it. Now let me tell you about this delta epsilon P, this plastic strain. You know this changes the stress. Means elastic strain will always change the stress. Now until it is elastic, all the strains are inelastic. There is no plastic strain. So everything was elastic. So all the stress change the stress. All the strain changes the stress. But once it cross the yielding limit, then there is a two-part. One will change the stress, which is the elastic part. So what does this plastic strain do? Plastic strain, what is its job? The plastic strain, they basically accumulate in that material. As you are giving load and load, it will keep on accumulating. And this accumulation causes basically the fractures. Maybe initially the internal fractures, and later on you will see the fracture on the surface also. And they changes the material. So if I can write it, this strain changes the stress, sigma. They changes sigma. And this one changes E. It changes the elastic properties of that rock or any other material. Okay? Sorry, this is P. Sorry. So the plastic strain increment that changes the property of the material completely. Okay, you started with the E and it does not change. Okay, now let me give you an example. You have probably done many times in your life. You take any plastic item, anything, and you give a fatigue load. Fatigue load means you do up and down like this. Okay, you give a once positive movement, then another time negative movement, and what do you see? That on that line where you are doing this by your hand, you know that plastic, you will see that initially the color changes, then you see initially first its color will change, texture will change, then gradually you will see a crack has developed. So this is nothing but you are accumulating the plastic strain in there. Okay, and as a result its E value is getting changed, and that is how basically ultimately the damage occurs in the material. So if I can give you an example, let's say in a strain softening case, this is E originally, and then gradually at this stage E will be like this, at this stage it will be like that. So this elastic property is getting gradually changed like this. So you see its slope changes. So this elastic property gradually changes. Okay. So the purpose of this plastic strain is to change its material properties like elastic properties like E, mu, all this. Okay. So I think this is what you have. We will do for chapter 5. And this is what you have in the syllabus. Okay. Okay. Now I will give you a problem. Everybody ready? You write it down. Okay. Or let me write also here. No. Let's say I am testing a cylindrical sample. Okay, a cylindrical sample, and the stress on this is 40 MPa. Modulus of elasticity is 5.7 GPa. Washout ratio is 0.28. Can you tell me what is the volumetric strain? Epsilon B. How to calculate volumetric strain? In your rock mechanics lab, have you calculated? They have given you data, volumetric strain. Anybody is doing that? Who is awake? Still there. Amardeep, are you still there? Ahmad. Ritik Raj. Nobody's there. Anybody else done? Nobody is in the other side.
Could you show the values once more?
Who is that? Dibba Sri.
And Divya.
Dibba, tell me how you have solved.
So like we'll apply the formula. We'll find the bulk modulus using.
Formula is this, right? This is the formula. Epsilon B is equals to epsilon XX plus YY plus JJ. Now, you can assume in any direction, it doesn't matter. This direction, and this direction. So let's say X, Y, and Z. Any three direction you take, one probably the particle. So from the data, this one is known very easily because epsilon ZZ is already given 40 by 570. This is in gigapascal, this is in megapascal, so I convert it. Now epsilon XX definitely minus mu into sigma ZZ. So, sorry, sigma ZZ by E. So this will be 40 by 570. This one is also same, mu into 40 by 570. So basically the formula is sigma by E 1 minus 2 mu. This is the volumetric strain formula. When you know when the stress is applied in one direction, let's say in this case the axial direction, and other two directions are free. Okay, their other two directions are free. Then this will be the formula. So now you have to, all the data are given, you have to just put those data and you can calculate. Okay. So I'm not sure in your lab experiment whether they have given you the data or whether you have calculated sigma and E and mu from your whatever the data they have given you. If they have given, then you will be also able to find out that at the failure, at the time of failure, what was the volumetric change or how much volume was changed before failure. Okay, so this will be directly, okay, this is a direct relationship with modulus of elasticity and Poisson's ratio. So these are the two elastic properties we will control this value. And that's why, again, it is shown the volumetric strain can only be 0, and that's why the mu value maximum can be 0.5, which will happen only in water. And that's why in water it is said it is incompressible. Water, you cannot change its volume. Okay, and that is the reason, because its mu value is 0.5. That's why whatever compression you give, its volume will not change. If you give in one direction, water will go in other direction. Okay, it will keep the volume same. Okay, but rock, volume change you cannot ignore. Okay, there will be a volume change. So there is a lot of porosity there. Okay, pore space is there. So volume is going to change. Okay, so I will. Yeah, go ahead. Any questions if anybody else?
There is this 1 minus 2 mu into 3 in the.
Into what?
Into 3.
No, 1 minus 2 mu into what you said?
So will it be 3 into 3?
Into 3? No, no, no. Okay. No 3. See, let me write the formula. See, this x and y is my free surfaces, okay, and in two directions. So this will be mu by sigma by E. Sigma is only applied in one direction. Remember that here. It's a injection. It's only one direction we have applied. Then again, this direction will also be same. And this is sigma by E. That's why sigma by E is common and 1 minus 2.
Yes, sir, I understood.
Okay. Because formula is epsilon xx plus epsilon y plus epsilon z. This is coming from Poisson effect. All right. So what I will ask you is go through chapter 5 and chapter 4 of the book. Try to solve the exercise. If you cannot solve, send it to us. We will help you. And then from next week, 3 to 4 will be the test. Okay. Is that clear? So you have 1 week to prepare. Let me take the attendance, then you will leave. Just a minute. Okay. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Yeah.
Thank you, sir.